Good morning, everyone. I am Venu Yatam, a final year CSA BTech student at IIT Bhubaneswar. I would be presenting on a paper named Self-Attention for Cyberbullying Detection on behalf of my supervisor, Dr. Padmalochan Bera. Cyberbullying has been defined as bullying through the internet or using social media, messaging, and gaming platforms, or more recently, mobile phones to repeatedly embarrass or hurt people. Cyberbullying has been a very important issue in the age of internet and digital revolution. Since the inception of social media platforms like Facebook in 2004 and Twitter in 2005, cyberbullying has been increasingly common. Cyberbullying has almost the same adverse level psychological impacts as offline bullying. The victims have potential chances of falling into prolonged depression and often isolate themselves from society or even entertain suicidal thoughts. The effects of cyberbullying have been more pronounced over adolescents and insecure individuals. In this context, cyberbullying detection becomes essential for ensuring social well-being. However, the task in itself is quite challenging due to its subjective nature and its association with diverse topics such as religion, gender, color, etc. Vocabulary and comprehension of words also vary over multiple social media platforms. Recent research using machine learning and deep learning models have yielded significant results aiding in timely detection and prevention of cyberbullying. Initial attempts at text classification by Kim et al. And subsequent works by Amir et al., Konay et al. Exemplified the efficiency of CNN architectures in solving sentiment analysis. Several works have also explored the usage of recurrent neural networks that capture temporal data dependencies. Classification of sentences made up of words arranged temporally inspires one to go in this direction of recurrent neural networks. In the context of text classification, these deep learning models have succinct representation for words called embeddings. Architectures like long short-term memory LSTMs as shown on the left, which are a specialized form of recurrent neural networks for comprehensive text processing with memory are used. LSTMs in particular have proven to be more efficient at handling machine translation due to their capabilities of learning long-term dependencies. As can be seen from the figure on the left, LSTMs have several entities like sigma, tanh, etc., which we shall not be going into further details. It is these complex components that make the long short-term dependencies work in LSTMs. A few works also explored convolutional neural networks for extracting 2D correlations between the contextual entities of text. A generic CNN architecture is as shown on the right. A CNN employs 2D kernels on an image, that is, a 2D or a 3D information to extract the correlational makeup features of the input. Recurrent neural networks or sequence models extract the temporal features of an input, whereas the convolutional neural networks extract and work on spatial features of an input. For the current problem, both the temporal and spatial correlation traits seem important. Zhou et al. Explores a hybrid architecture of LSTMs and CNNs. In their architecture, the input is represented in a 2D format and is fed to CNNs. The CNNs learn the spatial correlations among the input. These spatially learned features are fed to LSTMs as shown in the sequence manual. These LSTMs learn the temporal features from their input and give the output. A classification of 2D input fed to the CNNs is given as output by the series of LSTMs. Coming to our work investigates cyberbullying detection from the perspective of self-attention models in deep learning. Recent achievements of self-attention models in achieving state-of-the-art records for machine translation has been the major motivation behind this work. Such attention models are replacing the state-of-the-art recurrent neural networks for translation tasks. We explore the usage of these attention mechanisms instead of traditional recurrent neural networks like LSTMs for detecting cyberbullying from text input. We compare the efficiency of our model with that of the traditional machine learning models like SVM, logistic regression, etc., and with that of the aforementioned state-of-the-art deep learning models given in the related work. The attention mechanism in deep learning is a method to allocate attention values to various components of a system quantitatively. This method has shown excellent results in natural language processing and was introduced to address the problem of long sequences in language to language translation automatically by machines. Attention is a component of a network's architecture that quantifies the dependence of output on the input of a network. An attention function maps a query and a tuple of key value pairs to an output. Here, the weights assigned to each value is computed by a helper function with a corresponding key input. Finally, a weighted sum of the input values is given as output. In general, there are two types of attentions. First, just general attention. This kind of attention is between several input elements in a layer of a neural network. There are different types of attention mechanisms explored by various researchers. These attention mechanisms differ based on the alignment score, that is, the attention formula used by the helper function. Second type of attention is self-attention. Self-attention is an attention mechanism relating different positions of a single sequence in order to compute a representation of the same sequence. This is also known as intra-attention. We adopted a neural network architecture with attention mechanism given by Vaswani et al. This is called as the transformer model. The transformer uses the multi-head attention block. The attention mechanism in the transformer is interpreted as a way of computing the relevance of a set of values, that is, the information based on some keys and queries. The multi-head attention block computes multiple attention weighted sums instead of a single attention pass over the values, unlike traditional attention mechanisms. This is the reason it is named as multi-head attention. This is basically like using different filters in a CNN network for capturing different features between the entities in an image. To learn diverse representations, the multi-head attention applies different linear transformations to the values, keys, and queries for each head of the attention. This can be seen in the figure shown on the right here. And as for the type of attention mechanism, the transformer uses a particular type of attention called the scale dot product attention as shown on the left. This basic attention formula is simply a multiplication of the softmax dot product between the query and the key and the values. The scale dot product attention is an integral part of the multi-head attention used in the transformer model. The overall structure of the transformer architecture used is as shown here. The transformer architecture follows an overall standard encoder-decoder architecture, replacing the recurrent layers that are most commonly used in encoder-decoder architectures with multi-headed self-attention. Now, coming to the encoder. Encoder contains a stack of 10 fully connected layers in which each layer in turn has two sublayers. The first sublayer is a multi-head self-attention mechanism. The second layer is a feed-forward fully connected network. A residual connection is employed around each of the two sublayers and the normalization is used. The left half part of the network in the figure shown is the encoder. Now coming to the decoder. Decoder is also made of 10 identical layers. The decoder network has an extra third sublayer along with the two sublayers of the encoder network. This third layer performs multi-head attention on the output of the encoder. In the decoder 2, residual connections around each of the sublayers are employed and further is followed by normalization. The right half of the network figure shown here is a decoder. Positional encoding. As the architecture neither has recurrence nor convolution, in order for the model to use the order of the sequence, there must be some input about the position of tokens, that is, words in a post in the sequence. For this, positional encodings are added to the input embeddings at the bottom of the encoder and decoder stacks. The detailed inclusion of multi-head attention in both the encoder and decoder can be seen here in the figure. This work uses three open source datasets: Wikipedia, FormSpring, and Twitter. We use glow word embeddings on the words of all these three datasets. To the best of our knowledge, this is the first work that considers employing self-attention models and the transformer architecture of Google machine translation team to cyberbullying detection. Wikipedia dataset. This dataset contains around 100K labeled discussion comments from Wikipedia's talk pages. For every page in Wikipedia, a corresponding talk page maintains the history of discussion among users who participated in its editing. Each comment was labeled as illicit or non-illicit. FormSpring dataset. FormSpring is a social network based on questions and their corresponding answers. It was launched in 2009 and has been a standard dataset for cyberbullying works, which make us include this dataset despite it being old. An extended version of this dataset is available on Kaggle. The dataset was collected using web crawlers for 50 user IDs. Twitter dataset. This dataset contains 16K annotated tweets. The dataset is created by performing a manual initial search of common illicit words and terms used corresponding to sexual, gender, religious, and ethnic minorities and discrimination. A total of 16K tweets were selected for several users. We cover these three different types of social networks as each dataset has a different version of cyberbullying. Twitter, which is a microblogging platform, this Twitter dataset has samples of sexism and racism. Wikipedia, on the other hand, which is a collaborative knowledge repository, this dataset contains examples of personal attack. However, the FormSpring dataset is not specific in nature. All these three datasets suffer from the problem of skewed distribution or class imbalance, where the number of posts marked as cyberbullying is very less than that of the normal posts. So balancing has been done by using the traditional method of oversampling of the bullying examples. The size of each sample is measured in terms of the number of words in it. We take the maximum length of an input post to be 100. That is, a post can have a length up to 150 words, exceeding which the extra words of a sentence are mitigated. We then convert the words into known embeddings. We use global vector representation of words in which each word is represented by a one-hot vector. These one-hot vectors are fed into the model with optimized hyperparameters that predicts the probability of the post being abusive or not. Coming to the results, we take into consideration three parameters in experimentation: precision, recall, and F1 score. These values of a system for the three datasets versus different models is as shown in the table here. We note that SVM and logistic regression models require preprocessing and have lower precision and recall in comparison to those of the deep learning models. Among the deep learning models we used in our comparison with the self-attention model, BLSTM, bidirectional LSTM, with attention by Agrawal and Avekar, performs better than CNN and CLSTM models. However, the self-attention model outperforms the BLSTM model with attention. The precision, recall, and F1 scores for Twitter dataset are 89.7, 88.5, and 89.1% respectively, which are around 5 to 6% increase from the best model. In case of FormSpring dataset, these values are 89.4, 91.5, and 90.5% respectively, which are around 7 to 8% more than the best model's performance. Wikipedia data also exhibits a similar performance with corresponding values of 84.2, 83.8, and 84.1% respectively. Coming to the future work, evolution of communication and media over the internet has led to diversification in methods of initiating cyberbullying. One of the latest examples of such media is an internet meme. According to Wikipedia, an internet meme, or in short meme, is a piece of media traditionally combining image macros with a concept or catchphrase which is spread behind a meme is a challenging task and also varies over social and cultural context. Considering the importance of these facts and the virality in propagation of memes over the internet, it becomes a necessity to build cyberbullying detection systems adapted to handling the semantics of memes. We believe that hybrid deep learning models equipped with self-attention and the capability to simultaneously handle and extract semantic meanings from image collages, randomly placed text, or animated figures constituting a meme will provide better insights to detect cyberbullying. Our future work is primarily aimed in this direction. Timely inference with the capability of detecting and addressing the degree or severity of bullying is the main goal of fighting and preventing cyberbullying over the internet. Thank you.
So guys, as we were watching a video, unfortunately we cannot have questions now section, but if you have any questions or any suggestion, please send an email to the address your questions to the authors, okay?